In this question here, it says determine the equation of the vertical asymptote for this function where where our base is between 0 and 1. Just a quick reminder, if you have a base between 0 and 1, our graph should look potentially like this, starting off in quadrant 1, hugging that y-axis and turning away, descending. So that's usually what our graph is going to look like between 0 and 1 for a fraction. So first things first, I notice that this equation has not been factored, so I'm going to quickly rewrite it. So this is now y equals 2 log c of, well, you have a negative because we have to factor out a negative, x minus 6, double bracket close, plus 5. Let's take a look at our characteristics. We have a vertical stretch, we have a reflection, and this reflection, by the way, is on the y-axis. We have a horizontal translation, and this here minus 6 means we're going 6 to the right, and we have a vertical translation. This is 5 up. Okay, so if we're looking at vertical asymptote, I need to take a look at the characteristics here. So I have 4 of them, and which out of these 4 would affect my vertical asymptote? So currently my vertical asymptote is at x equals 0. There should be a dotted line right here if I didn't do anything to my graph. So there is a dotted line right there. So vertical stretch, does that affect our vertical asymptote? No, it doesn't. It doesn't do anything. Reflection changes the graph but doesn't change our asymptote. Horizontal translation, 6 to the right. There we go. That's the one that's going to change our graph. So here, if I have 6 to the right, that means my vertical asymptote was moved 6 to the right, and my graph will look something like that. So therefore, our vertical asymptote is at x equals positive 6 because we moved it 6 to the right. In number 7 here, it says determine the domain and range of this function, again where we have a condition of c being between 0 and 1. Again, if we have a condition of between 0 and 1, again my graph should look something like this, hugging that y-axis, going down, turning away, descending is what it should look like. Let's take a look at our equation. It hasn't been fully factored, so let's start there first. So we have y equals log base c of negative 2 bracket x plus 4 close close plus 4 again. So what do we have? We have a reflection, and this one's on our y-axis. We have a horizontal stretch by a factor of 1/2. We have a horizontal translation by a factor of 4 to the left. And of course we have this last 4 here, which is a vertical translation, 4 units up. So let's take a look at our domain and range and what's going to happen. So if I start applying some of these here, my original graph, if I reflect it over my y-axis, it's going to now look like this here. If I have a horizontal stretch by a factor of 1/2, it's basically the same graph, it's just slightly shrunken. I'm going to move it 4 to the left. So if I moved it 4 to the left, I have a vertical asymptote here, and our graph was moved 4 to the left, so it's going to look something like that, and 4 units up. And again, you have that vertical asymptote that was moved 4 left, and if you're 4 up, you're going to look something like that, a bit higher than the previous. Okay, so let's talk about domain and range on this one. So our domain is as far left as negative infinity and as far right as wherever that vertical asymptote is. That vertical asymptote is at 4. And you can't include it because it's a vertical asymptote. Our range on this one is going from negative infinity all the way up to positive infinity because it's going to go on forever. And there we go. And that's our domain and range for this one. In example 8, before we get there, we're just talking about transformation. So if I have a log x equation, log base c of x equation, I can use the transformations a, b, h, and k to make a new equation. All the characteristics are still the same: vertical stretch, horizontal translation, and vertical translation, all in that order. So number 8 says we have log base 3 of x, and we have a bunch of these transformations occurring to it. Write down the new equation. So what's our new equation? It's going to be y equals, we have a vertical stretch by a factor of 3, so that's going to be 3 here, reflected on the x-axis, so that 3 is now negative 3 because we're reflecting it. We have our log base 3 of x, but this x value here, what are we doing to x? We have it translated 2 units, right? So that's going to be minus 2. And at the end of all that, we're going to go plus 4 to go 4 units up. So here's our new equation. We're going to sketch this new equation, and what I would strongly advise you to do is do this on your graphing calculator. But the first thing before I switch over to my graphing calculator is I'm going to draw in my vertical asymptote. So my vertical asymptote again is based off of my horizontal translation. If I'm moving it 2 to the right, my vertical asymptote got moved 2 to the right as well. So it's going to go straight down x equals 2. For the rest of this, I'm going to switch over to my graphing calculator and see where our coordinates are. And here we go. I just have my graphing calculator loaded up, typed in my equation here, and I should be good to go to graph. I'm going to hit graph, and that's my curve there. I'm going to go second graph to see if I could pull off some coordinates. Of course, I have errors everywhere past smaller than 2. Well, at 2 we have our asymptote, everything smaller than it, our graph doesn't exist, so it's going to error out. The first coordinate I want to put down is 3, 4, and then 5, 1. So 3, 4, and 5, 1 are good coordinates to use. So 3, so 1, 2, 3, 4. Oops, let's get back to our marker. It's 3, 4, 5, 1. And let's see, do we have any other good coordinates? Doesn't look like it, but we do go negatives. 11 and negative 2 is in the next closest one, so 11, 10, 11's off the grid, negative 2 just slightly below. So there we go. Trying our best to connect our dots. We have about 3 of them that we're going to try to use. And here we go. And there's our graph. Its characteristics, let's take a look. So domain, as far left as we can go was positive 2, as far right as we can go, infinity. Range, the lowest is going to be negative infinity, the highest positive infinity. X-intercept, we definitely have one. Again, I'm going to go straight to my graphing calculator, look right here. To figure that out, I'm going to go second trace, option 2, go left of where I think it is, hit enter, go right of where I think it is, hit enter, and guess where I think it is. And so we have a x-intercept at 6.33, 6.33 and 0. There we go. No y-intercepts, so I'm going to write down none here. And equation of asymptote, well, which one do we have? We have a vertical asymptote. So I'm going to write down vertical asymptote. And this is at x equals positive 2. And there we go. At the bottom of this, it asked us to write down the mapping notation. So x comma y is going to become x plus 2 because we are shifting it 2 to the right. And we have minus 3y plus 4 for the rest of our equation. And so there we go. That is my graph with the x-intercept. In example number 9 here, we're giving you two graphs. I'm giving you f and g of x. So I gave you two graphs there, and g of x might be hard to see. But I gave you two, and I'm asking you to go from f of x to g of x. What's the equation? So first things first, what you want to do is compare coordinates. And you kind of want to do this also running in the back of your mind RST. Okay. It also says that the graph of the function of log base 2 of x is given to you, so that's f of x, and g of x is the transformed one. So for a here, we definitely have a reflection because it changed direction. So let's jot that down. So we have a reflection on our x-axis. So we have reflection. We only have the one. If it was a double, it'd be going towards either quadrant 2 there or quadrant 3. But right now we have a single reflection right over that x-axis. The next thing I notice is I'm going to check for any stretches. So let's take a look at some coordinates. Some normal coordinates that we have is going to be at 1, 0, and both look like they're crossing through 1, 0. For f of x here, I have 2 and 1, 4 and 2, and of course 8 and 3. So those are my three coordinates there. Let's take a look down here. I have a good coordinate at 2, and it looks like that's about 2 and -3. There we go, and the last one here. There we go. Okay, so comparing our graphs. So again, we have an intercept there. Let's take a look at any vertical stretches first. Well, I have a stretch of distance of 1, distance of 2, and a distance of 3, comparing it to my first coordinate here. From my first coordinate here, I have a distance of 3, 6 away, 9 away. So again, my distance here was 1 away, 2 squares away, 3 squares away. So 3, 2, and 1. That's my original. And we're hoping that it was the same pattern, otherwise we have a vertical stretch. We have 3, we have 6, and we have a distance of 9 away. So we definitely have a vertical stretch. The question is by what factor? This is a vertical stretch by a factor of, well, instead of going 1, 3, and 1, 2, 3, we went 3, 6, 9, so it's going to be by a factor of 3. Do we have any horizontal stretches? Well, let's take a look. Well, the difference between the first coordinate and the second one is 1 square away, 2 squares away, and here, so this is really 1 square away, 3 squares away, and this here is 3, 4, 5, 6, 7 squares away from the original or from the invariant point of 1, 0, or really it's about 1, 2, 3, 4 squares away difference there. So we went a difference of 1, 2, and 4. Let's see if that holds up here. We have a difference of 1, we have a difference of 2 squares, and we have a difference of 4 there, so it does hold up. So no horizontal stretches, so just our vertical stretch. So to rewrite our equation, it's going to look something like this. We have g of x is equal to, well, we have a reflection, so that's negative. A vertical stretch, that's 3 log base 2 of x. And so that's my equation there. Let's take a look at this equation over here. Let's see if we can pick out some good coordinates. So again, I'm at 1, 0, that's a good one. 2, I'm at 1, 3, 4, 4 looks like I'm at 2, 5, 6, 7, 8, 8 looks like I'm at 3 again. Okay, so those are solid coordinates to choose. Over here, I'm not at 1, 0 anymore, I'm at 1, 2 it looks like. And here, about 2 higher, 2 higher, and 2 higher here. So right away, let's double check RST. R, do we have any reflections? No reflections in this case. So I'm going to write down no reflection. S, do we have any stretches? Let's double check. So our stretches vertically, we have a difference of between here and here is 1, between here and here is 2 squares away, and 3 squares away on the original. On the new, I'm 2 squares away, looks like 3 squares away, and 4 squares away. So right now, there's no consistency. If there was consistency, you'd have a vertical stretch, but there's no vertical stretch. And also, if we had a vertical stretch, it should have gone through an invariant point of 1, 0 and then stretched out. But in this case, because there's no invariant point as well on g of x, it didn't go through the same invariant point, that is, there's no vertical stretch. Let's take a look at horizontal stretch. Horizontally, we're going, again, horizontally you want to compare coordinates, that is. So if you took this one to this one here, let's compare. So this is a difference of 3, 1, 2, 3 squares there. The next one, to go from here to here, that's a difference of 1, 2, 3, 4, 5, 6, difference of 6, difference of 3. So most likely we have a vertical stretch, and it's going to be by a factor of, and this is a half here, 1.5. Looks like it's stretched 1.5. So most likely we have a horizontal stretch, and we could say that's almost by a factor of, not 3, but this is at 1 we went to 4, at 2 we went to 8 there, so it's by a factor of 4. So we have a horizontal stretch by a factor of 4 if we're going from g of x to f of x, but by 1/4 if we're going from f of x to g of x. So we're shrinking it down by 1/4. So right away we have one equation here that we can write down. It's a horizontal stretch by a factor of 1/4, which is now y equals log base 2. If it's 1/4, I have 4x right here. And that's our equation. The other way that you could have done this, instead of doing the horizontal stretch, by the way, is taking a look at our coordinates. And this is probably the more obvious one that most people did. Again, 2, 4, and 8. I just had coordinate dots right above it. Here, we're just moving everything the same distance away. And that's a vertical distance, by the way. Here we can say we have a vertical translation 2 units up. That would also be the exact same. So here I can write down an equation based on this info as y equals log base 2 of x, and then we have plus 2 because we're moving everything 2 up. So both of these would net you the same equations. But yeah, there's just 2 different ways to approach this one. Last but not least, we got number 10 here. So number 10 is our word problem for today. So the word problem is frequency of a musical note can be determined by this function here in the number of notes away from A for 40 hertz. And F is the frequency of the note in hertz as well. The lowest note on a guitar has a frequency of 82.407 hertz. Determine how many notes away from A it is. Okay. So if we know our frequency, let's plug it right into our equation there. So I'm going to rewrite n equals 12 log base 2, and in bracket here we have our 440 in our denominator and this 82.407 in our numerator. Let's close bracket. Once you type all this into your calculators and solve, you should end up with negative 28.99 basically, or minus 29. So how many notes away from A are you? You're 29 notes away. So therefore 29 notes away. And yeah, so that's the first one. Second one, find the frequency of a note that is 6 notes above A. So this is, sorry, in my previous answer I should have wrote 29 notes away slash, or it's 29 notes below A. instead of away. Below would have been a better descriptor based on this next question here. So if we were 6 notes above, basically I'm going to rewrite this equation as 6 equals 12 log base 2 of f, and that's what we want to find, frequency of 440 on our denominator. There we go. So how do we find this? Well, first off, I'm going to isolate this equation by dividing both sides by 12. So I'm going to divide by 12, divide by 12. This gets me to 1/2 here on the left is equal to log base 2 of f over 440. Switching this back into exponential, this is now base 2 to the 1/2 is equal to f over 440. And from here, I want to isolate for f by multiplying 440 out. So f equals 440 multiplied by 2 to the half. Working on our graph calculator, you should have ended up with 622.25 hertz. There we go. If you have any questions about today's lesson, please feel free to ask.